For generations, humans have imagined what life might be like in other universes. Thanks to the James Webb Space Telescope, JWST, the most advanced and shocking telescope ever built, we're now closer than ever to exploring that question. While observing Proxima Centauri, the star system nearest Earth at just 4.2 light-years away, scientists noticed several strange anomalies coming from one of its planets, Proxima B. These anomalies, described as potential artificial lights, have baffled leading experts. What exactly are they? Could they point to intelligent life? Join us as we examine the James Webb Space Telescope's unsettling discovery, city-like lights that could change everything we know about life in the universe. Until now, Earth remains the only known home to life. But since the dawn of civilization, people looked at the stars and wondered, are we alone? To seek answers, American cosmologists Jill Tarter and Thomas Pearson launched a search for extraterrestrial intelligence, SETI, project in 1984. Its main objective was to detect radio transmissions from space, signals that could travel vast distances and be picked up by the 42-dish Allen telescope array nestled in the Californian foothills. Yet, for over 3 decades, no clear extraterrestrial signals were found. Then came a breakthrough, the launch of the James Webb Space Telescope. As the largest and most sensitive telescope ever deployed, drifting about 1 million miles from Earth, it brought unprecedented power to study distant exoplanets invisible to previous telescopes. A few decades ago, no planets beyond our solar system had been confirmed. Today, over 4,000 exoplanets have been discovered, orbiting stars across the galaxy. According to NASA, the universe could hold trillions more. Among the early signs of alien life may be vegetation on these distant worlds. For example, when the Galileo spacecraft passed Earth on its way to Jupiter, it turned its senses back and detected the vegetation red edge, a strong combination of red and near-infrared light reflected by plant life. If another planet were covered in greenery, we might recognize this same spectral signature. The JWST is designed to detect such signals on Earth-like planets in habitable zones, providing potential evidence of life-supporting atmospheres. As light from a star passes through a planet's atmosphere, certain wavelengths are absorbed by the elements present, leaving behind identifiable gaps or fingerprints in the light spectrum. Using spectroscopy, JWST can decode these patterns to determine what gases are present: oxygen, nitrogen, carbon dioxide, or more exotic chemicals. This could reveal not only conditions for life, but even signs of intelligence. For instance, industrial chemicals like chlorofluorocarbons, CFCs, used in refrigeration and cleaning, are synthetic and wouldn't exist naturally. Their detection in a planet's atmosphere could indicate advanced civilization. Of course, life on exoplanets might look nothing like life on Earth. Some organisms, like extremophiles, survive where others can't, in boiling heat, freezing cold, or highly acidic environments. These alien microbes thrive in conditions once thought uninhabitable, broadening our idea of where life might arise. That said, scientists are first focusing on planets with milder, Earth-like environments, ones with stable temperatures and liquid water orbiting calm, long-lived stars. While our own sun is a yellow G-type star, relatively rare and short-lived, red dwarf stars are far more common and longer-lasting, making them promising candidates for the search for life. The likelihood of finding planets orbiting red dwarf stars is relatively high, as these stars are cooler, dimmer, and more common than our sun. Their long lifespans provide a stable environment for life to potentially emerge and evolve into complex organisms. One of the key targets for the James Webb Space Telescope, JWST, is the TRAPPIST-1 system, located about 40 light-years from Earth. This system consists of a calm red dwarf star, surrounded by 7 rocky, Earth-sized planets. 3 of these planets lie in the so-called habitable zone, where liquid water could exist on the surface. Despite being smaller and colder than our sun, the TRAPPIST-1 star emits light sufficient to warm its closely orbiting planets. Another compelling candidate for the search for extraterrestrial life is Proxima Centauri, a red dwarf star just 4.25 light-years away. Proxima Centauri is much dimmer than the sun, so any potentially habitable planet must orbit much closer to it. In August 2016, astronomers discovered such a planet, Proxima B, which has about 1.3 times the mass of Earth and lies within Proxima Centauri's habitable zone, a Goldilocks zone where the temperature is just right for liquid water. However, Proxima B may face significant challenges. It orbits extremely close to its star, just 4.66 million miles away, which likely causes it to be tidally locked, always showing the same face to the star. This close proximity also means it's constantly bombarded by powerful stellar winds, which can strip away its atmosphere. Yet, due to its nearness to Proxima Centauri, Proxima B receives enough light to maintain temperatures that could allow for liquid water, assuming it retains an atmosphere. Proxima Centauri has only about 18% of the Sun's mass and emits just 5% of its light. Despite this, Proxima B could still harbor water if an atmosphere exists to trap heat. The total energy the planet receives is around 65% of what Earth gets from the Sun. Still, tidal locking may lead to extreme temperature contrasts, a scorching day side and a frozen, dark night side. Adding to its woes, Proxima B is bombarded with about 5 times more high-energy radiation, including X-rays and ultraviolet rays, than Earth. Violent stellar flares from its host star further intensify this radiation. If Proxima B lacks a strong magnetic field, it may be unable to shield itself from this onslaught, making the environment less favorable for life. However, if it possesses a protective magnetic field and volcanic activity that replenishes its atmosphere, like Earth, then habitability becomes more plausible. Unfortunately, we currently have no data on Proxima B's volcanic behavior or magnetic field strength, so the existence of an atmosphere remains uncertain. Yet the presence of an atmosphere is a critical indicator of a planet's potential to support life. Some speculate that Proxima B might host advanced technology, such as solar panels on perpetual day side, to generate energy that powers lighting and heating systems on the dark side, an otherwise uninhabitable zone, due to extreme cold and lack of sunlight. The discovery of Proxima B has spurred efforts to determine whether it transits its star as seen from Earth. If it does, astronomers could measure the planet's size, mass, and density, confirming its rocky composition, and even analyzing its atmosphere by examining how starlight passes through it during transit. However, the odds of a perfectly aligned orbit that allows a visible transit from Earth are slim, only about 1.5%. Additionally, Proxima Centauri's tendency to flare unpredictably complicates observations. According to David Kipping, an astronomer at Columbia University, Proxima is an unstable star. Still, rocky planets like Proxima B absorb stellar light and re-emit it as infrared radiation, a signature that JWST was specifically designed to detect. Observing Proxima B's infrared emissions could provide critical insight into the planet's composition and potential for hosting life. The James Webb Space Telescope, JWST, with its superior infrared capabilities compared to Hubble Space Telescope, may be able to detect artificial lighting on the night side of distant planets, potentially even city lights as faint as those on Earth. If such lights are limited to a narrow frequency band that doesn't overlap with the star's natural emission, the JWST could pick them up. Proxima B's day side might be densely covered with solar panels, reflecting starlight in a way that indicates technological activity. Because the planet is tidally locked, meaning one side always faces its star, it likely experiences extreme temperature differences between its day and night sides. The degree of that contrast depends on whether Proxima B has an atmosphere or circulating water to help distribute heat. Without an atmosphere, the day side would radiate all received energy as infrared light, while the night side could resemble a frozen wasteland. However, if temperature differences are less stark, it could suggest the presence of an atmosphere, an essential condition for potential habitability. As the JWST continues its search for exoplanets, it could be the key to detecting life beyond Earth, possibly even intelligent life. Still, we must recognize the limits of current technology. While the JWST is a monumental leap in space observation, it marks only the beginning of our deep space exploration journey. Challenges like vast distances, unpredictable stellar activity, and atmospheric interference mean that we may not always receive clear or conclusive data from far-off worlds. Nevertheless, the potential for groundbreaking discovery remains vast. As we enhance our tools and refine our methods, we move closer to uncovering signs of life. The ongoing study of Proxima B and similar exoplanets continues to push the frontiers of science. Each new piece of evidence, be it atmospheric clues, water signatures, or hints of artificial illumination, brings us closer to answering one of humanity's most profound questions. Are we alone? With the JWST's advanced capabilities, we are on the verge of glimpsing far beyond our solar system in search of life and, perhaps, signs of alien civilization. The years ahead promise exciting developments as we learn more about the atmospheres, compositions, and potential biosignatures of exoplanets like Proxima B. Whether we discover microbial organisms or intelligent life, the age of cosmic exploration has only just begun, and its possibilities are nearly endless.